Section 4.4 is the optimization problems section. And what this does is it uses real-world examples, and you find the critical values and the mins and maxes. So that's what optimization means, is it finds the minimum and or maximum values of a function. So to do an optimization problem, you need something to take the derivative of, and you need to set the derivative equal to 0 or find out where it's undefined. We can use that to find our critical points and our extreme values. This is kind of the procedure. You can find this in the book as well. The first thing you should do is read the problem carefully and identify the variables. It helps to draw a picture a lot of times. So if possible, you should try to draw a picture. It helps you organize the information. The second thing to do is identify the objective function. Objective function means it's the object of our work. We're going to optimize this function. The third thing is identify constraints. There are certain things that have to be true. Those things that have to be true can be put inside the function so that we can do step 4. We can use those constraints so that the objective function only has one variable in it. So when I take the derivative, I don't have to do anything funny. In step 5, identify the interval of interest. These are real-world problems, so you have to think about what can happen and what can't happen. That's what the interval of interest means. And the part 6 is where you actually take the derivative to find the extreme values. And you find the critical points with the derivative, and then use those to help yourself find the extreme values. So I have a couple examples here I want to work through from 4.4, but the same idea for all these examples. The first one says, what two non-negative real numbers with a sum of 23 have the largest possible product? And there's two things we need here. We need a function to find the derivative of that we're trying to optimize. A lot of times you'll see largest, biggest, smallest, least, maximize, minimize. Those are types of words to let you know where the objective function is. Here, the objective function is the product of two real numbers. So I need two non-negative real numbers. I'll call the first one x. That'll be my first number. And my second number will be y. And the objective function is the largest product of these two numbers. So the objective function that I want to make the biggest to the smallest is the product. I'm going to call it P for product. You didn't have to do this. But I get the product. That's just x times y. I want that to be as big as possible. So I'd like to take the derivative of that. But the problem is there's three letters there. There's a P, there's an x, and a y. I'd like to get rid of one of those x's or y's, so it's easier to take the derivative here. So that is where you can find the constraint. The constraint equation is the one that has numbers in it, that's already been solved. In this case, the real numbers have a sum of 23. So I know that when I add x and y together, I'm going to get 23. I can't optimize the constraint equation because there's already a number that it's equal to. The product, I don't know what it's equal to. The constraint has to be 23. So I can take this constraint equation and solve it for one of the variables. I'm going to solve it for y. And then I'm going to take that and I'm going to plug it in wherever I see y. So now I can rewrite my objective function in terms of a single variable. And that's what they mean with step, I think it's 4. Use the constraints to write the objective function in terms of a single independent variable. I got rid of one of those letters by solving the constraint for one and plugging it in. And so I end up with P is 23x minus x squared. Now that's what I want to optimize. So I take the derivative of that, and I get 23 minus 2x. Well, that's defined everywhere. So to find my critical point, I take 23 minus 2x, and I set it equal to 0. 23 is 2x. So 23 over 2 is x. The first real number has to be 23 over 2. To find y, I have an equation right here that relates x and y. Y is 23 minus x, and we just figured out that x is 23 over 2. And when I work that out, I get 23 over 2 for y. So the first number is 23 over 2, which is 11.5, and the second number is 23 over 2. So notice that it's a square is what this kind of tells us. If you want the biggest product, the sum you can think of as similar to a perimeter. But in this case, I solved the constraint for y, plugged it in, and took the derivative, and I maximized it. X is 23 over 2, Y is 23 over 2. That's as big as possible. We do know that these are real numbers and they're non-negative, so it had to be bigger than 0, and it had to be less than 23. Less than or equal to 23. Problem 2 talks about an airline policy, and it states that all luggage must be box-shaped with a sum of the length, width, and height not exceeding 108 inches. What are the dimensions and the volume of the largest square base box with the greatest volume? So I'm going to draw a picture here. It's a square base box. So it's a box that has a base that's in a square. So I'm going to call those X. And then the height, it doesn't matter what the height is. You can have any height. So I'll call the height Y. Now it says that the sum of the length, width, and height will not exceed 108 inches. So at the maximum, it's going to be equal to 108, because we want it to be as big as possible under these constraints. Or 2x plus y is 108. That has to be the constraint because it's solved for a value. You can't make it bigger or smaller. And the thing we want to maximize is the dimensions and the volume with the greatest volume. So we want the volume to be the greatest, so the objective function has to be the volume, which is x times y. We don't know what the volume is. That's what we want to maximize. And we can think about what can be true here for the sides length, width, and height. If we think about it, the sides of this box have to be bigger than 0, and they have to be less than 108 inches for these all to add up to that. So you know that our interval, well, we'll look at it in a minute, has to do with those numbers. So I'm going to take my constraint and solve it for one of the letters. In this case, I get y as 108 minus 2x. And I can plug that in to my objective function. So I get x squared times 108 minus 2x, which is 108x squared minus 2x cubed. Now that I have it in terms of a single variable, I can look at where it makes sense. These are the x values. The x values have to be bigger than 0, otherwise I can't make a box. And if I have to add all these up and get up to 108, there are two x's that I add up. 2x plus y equals 108. So half of 108, which turns out to be 54, x has to be smaller than 54. Because 2x, if I put 54 in there, equals 108. So this is kind of the stuff that makes sense for the values of x. I take my objective function and I find the derivative. I get 216x minus 6x squared. That makes sense everywhere. So I take my derivative and I set it equal to 0. I can factor out a 6x, and I get negative x squared plus 36x, or plus 36, sorry. And so I can solve this. Either 6x is 0, in which case x is 0, or negative x squared plus 36 is 0, which means 36 is x squared, and plus or minus 6 is x. So the critical points I get are 0, negative 6, and 6. But to build a box, the x has to be bigger than 0. Otherwise you can't build a box. And x can't be negative because I can't have a box with a negative side length. So all that's left is x equals 6. So I know the x dimension is going to be 6 inches, because all my widths and stuff are measured in inches. To find y, I can use the equation I have above. Y is 108 minus 2 times x is 6. And so if I plug that in, 108 minus 2 times 6, I get 96 inches. So the dimensions are 6 by 6 by 96 inches. To find the maximum value, I do x squared y, which is 36 times 96. And that gives me the largest volume, which is 3456 inches cubed, because it's a volume. So this is the max volume of 3456, and here are the dimensions. Oh, the next problem is similar. This is a really good one to know how to do. It's a nice one to show up on tests. It says, what are the dimensions and the area of the largest rectangle constructed with its base on the x-axis and two of its vertices on the parabola y equals 16 minus x squared? If something like this showed up on a test, I would be nice enough to draw a picture for you. And here's what the picture will look like. Here's the parabola 16 minus x squared. And the y-intercept of this thing happens at 16. And what we're doing is we're building a rectangle inside of this. Two of the vertices are going to land on the parabola. The other two are going to be on the x-axis. So this is the rectangle I want to build. This is the one that I'm looking to construct. And in general, to figure out how big these are, well, usually we measure x's from the origin. So if I was trying to find the area of this thing, the length of this thing, or the width of this thing is going to be 2x. And the length of this thing is going to be y. So the thing I want to maximize, I want the area of the largest rectangle. So the objective function I want is the area function. The area in this case is 2x times y. It's 2x because I doubled the base there. And there's supposed to be a constraint equation somewhere, and the constraint equation actually comes from the parabola. I know that the point on that parabola is usually given by xy, but I know since it's on the parabola, y is really just 16 minus x squared. I can replace the letter y with 16 minus x squared. So this becomes 2x times 16 minus x squared. So this is my constraint here. It allows me to replace the y with stuff with x's in it. And so here I get 16 times 2 is 32x minus 2x cubed. That's a polynomial and it's defined everywhere. So I set it equal to 0. And so I solve this I factor out a 2x. And I get 16 minus x squared equals 0. So either 2x equals 0, which means x equals 0, or 16 minus x squared is 0, which means that x is plus or minus 4. Those are my critical points. I got 0, negative 4, and 4. Now notice very quickly that if I'm thinking of the x value as how far I move in the positive direction, x can't be 0. If x was 0, I'd have no rectangle. That would be the minimum volume, which would be 0. And I don't want to think of x as being a negative number. I want to think of x as how far out I move on the axis. So 4 is the critical point that works. So I know that x has to be 4, and that means y, which is 16 minus x squared, (2xy) minus 2x cubed. It's plus or minus 4. So when I want to find y is 16 minus 4 squared, which is 0. So the point I get is 4 for x and 0 for y, which also doesn't work out. Yeah, so the area is going to be 2x times y, and y is 16 minus x squared. So I have the area, 32x minus 2x cubed. take the derivative of the area. There's my problem. I have to take the derivative before I do this stuff. No wonder it was working out funny. Ah, mistakes in math. Don't worry, if you make a mistake in math, someone has already made it before you, so it's not like you were the first one. Here's my objective function with a single variable, but I have to take the derivative to come up with the critical point. So it's 32 minus 6x squared. There we go, there's my derivative. And it's a polynomial, so I can set it equal to 0. I get 32 equals 6x squared. 32 over 6, which is 16 over 3, is x squared. So plus or minus square root of 16 over 3 is x. So I have two critical points. By the way, that's plus or minus 4 over root 3, or 4 root 3 over 3. So I got negative 4 over root 3 and positive 4 over root 3. Notice that x is going to be measured from the positive distance, so I use positive 4 over root 3 as the x value. The y value is 16 minus x squared, so I replace my x with 4 over the square root of 3, and I get y as 16 minus 16 over 3. 16 minus 16 over 3 into the calculator gives me 32 over 3. So now I know the dimensions of the largest rectangle and the area. Remember, the width of this thing is 2x and the length is y. So if I want to find the width, that's going to be 2 times x, which is 8 over root 3. If I want to find the length, that's just y, so that's 32 over 3. And so those are the dimensions of the largest rectangle. The area is the width times the length, 2xy. So I get 8 root 3 times 32 over 3. That's 256 over 3 root 3. And there are no units, so I can't go any further with my answer. But I have the dimensions, and I have the area that go with the largest rectangle. The same process, take your objective function and plug it in to get a single variable, take the derivative, and set that derivative equal to 0. So one more of these. It says find the point in the parabola nearest to 1, 1. And this is the same kind of thing. They're looking for something that's nearest. So my objective function is going to be the distance, because the distance tells me how close and far something is. Well, to find the distance, I need 2 points. One of the points, and this will be my second point, or my first point, that's the one we want to be close to, that's 1, 1. My second point is just a generic point on the parabola. I'll call it xy. But since we're on the parabola, I know that y is 1 minus x squared. That's my constraint that lets me solve for a variable. So I plug it in. So the distance is the square root of x2, which is x, minus x1, which is 1 squared, y2, which is 1 minus x, minus y1, which is 1 squared. And so the objective function I get as this is the square root of x minus 1 squared plus, notice y is 1 minus x squared, so I replace it with 1 minus x squared, plus x squared squared, which is the square root of x minus 1 squared plus x to the 4th. So I found my objective function, which was the distance, except I replaced y with 1 minus x squared. And so I get my objective function as x minus 1 squared plus x to the 4th all to the 1/2 power, because that's what the square root is. So now I find the derivative to find the critical points. To find the derivative, I need the chain rule. I get 1/2 times x minus 1 squared plus x to the 4th to the negative 1/2. The derivative inside is 2 times x minus 1 plus 4x cubed. So I can simplify this. I get 2x minus 2 plus 4x cubed over 2 times, that's the negative 1/2, so the square root is in the denominator. Notice I can cancel a 2 out of all the stuff on top. I get x minus 1 plus 2x cubed over the square root of x minus 1 squared plus x to the 4th. And that's my derivative. Notice it's hard to make the bottom of that thing 0. When I raise something to the 2nd power and the 4th power, it's always positive. So it's impossible for the bottom to be 0 here, because I'm adding 2 non-zero numbers. I can't put in 0 for x. So to find the critical points, I take this derivative, I'm going to write it as 2x cubed plus x minus 1 over the square root of x minus 1 squared plus x to the 4th. And I'm going to set it equal to 0. Now I can find my critical points, but to do it I'm going to clear the denominator by multiplying both sides by the square root of x minus 1 squared plus x to the 4th. And on the left-hand side they cancel. And I'm left with 2x cubed plus x minus 1. On the right-hand side I get 0. This one's a tricky one to solve. It's not a simple one to factor. What you can, though, is you can solve graphing on the calculator. That's one way to solve these types of problems that you don't know how to do algebraically necessarily. So what you do on your calculator is you enter into the y equals 2x cubed plus x minus 1. And notice this 0 is where you put your y. So where y equals 0 are the x-intercepts. So you can find the x-intercept of this thing on a graph. You can do it by tracing, you can do it by locating the 0, but the x-intercept to that function, when I plugged it in and checked it, I got that the x-intercept I'm looking here now, I go to the 0 to figure out what the x-intercept is, and it gives me 0.58975451. From the graph, I got that solution as that point for x. So I know that on the parabola, the x value is 0.59, all right? To find the y value, the equation of the parabola is 1 minus x squared. So to find the y value, I plug it into 1 minus x squared and see what I get. Now I typed the whole thing into my calculator just to get my answer as close as possible. I get 0.652189679. So there's the point on the y-axis, there's the point on the x-axis. So the closest point on the parabola 1 minus x squared to 1, 1 is this point here. 0.58975451, 0.6521896179. Another one of those optimization problems. Again, we get an objective function and the constraint function. Get rid of a variable and take the derivative.